Who's ready to go? Oh, me too. Great. Let's go. Okay, so hello, everybody. Thank you for coming to my talk on Java in the world of containers. This is talking about Java, the language and runtime in containers, as in Docker containers. So if that's not what you're expecting, stay and you'll learn something new. I introduce myself. This is me on a good day. This is my Twitter handle. Later, after the talk, I'll put the slides and the code and the Docker files onto Twitter. So you don't need to take photos unless you want to. Wait, take a photo of this one. That's a good idea. I run a Java user group in the UK, Southwest Java. If you come to the UK, you're very, very welcome to join us in Bristol, Southwest England. This is the company I work for. Does anybody know this company, Twilio? Woo! Hello, everybody. So for those of you who don't know, we make products. We make an API so that from your code you can make phone calls, send SMS, send faxes, send email. We also make really cool stickers, and I have a pile of stickers down here for you after the talk. So you stay to the end, then you can have a sticker. How about that? But this talk's not about Twilio, so that's the last I'm going to say about Twilio. I'm going to talk about containers, right? So what even is a container? Maybe you could give me a show of fingers from like one finger, I don't really know, to 4 fingers, I'm an expert. How well do you know containers? Lots of 2s, there's a 5. Some 1s. Okay, great. All right, so for that kind of average understanding which you just indicated to me, I will say like people think containers may be like small VMs, small virtual machines, but that's not really accurate. There are some similarities and there are some differences. A container is a set of features of the Linux kernel which can be used to provide a sandbox for a process. Okay, so if I run Java minus version, oh my goodness. If I run, then there's a Java process running on my laptop, okay? If I run the same, but in a container, again, there's a process running on the laptop. It's the same operating system, the same hardware. There isn't what there is in a VM, which is like an extra layer of virtualization. What you get with a container is a sandbox for a single process. So it may have a restricted view of the hardware capabilities of the machine. It may have a restriction about being able to do certain network operations, certain view of the file system, isolation from other containers. That's the point. But it is not the same as a VM. It's a process running on the host. The other thing that you need to run a container is this image, this idea of an image. So an image is somehow all of the files that you need to run that process. So the sandbox means you don't have, by default, any view of what's already on the machine. You have to bring everything yourself. Images are composed of layers. So this is a simple Docker file for running a Java application. You'll see it again in about 10 minutes. These are layers. Each layer is stored separately. And then the layers are arranged like this, bottom up this time. They're built on top of each other, and each layer is read-only, apart from the very top one, which is read-write, kind of copy-on-write layer. So that means that 2 containers running the same image, if one of them writes to the disk, the other one can't see it, right? But it also means these are read-only, so these can be shared between the containers, but they can't interfere with each other. And that will become important. You'll see why that's important later on. Sorry. Next. That's all I'm going to say really about the technical details of containers. If you want to know more, I really recommend this talk by Jess Frazell. It's from LinuxConf Australia last year. If you have 55 minutes of your time and you want to understand containers really, really well, this talk is excellent. I'll let you all take a picture of that. Okay. So what else? We have containers. Now we need to know what is a Java. And the Java that you love and I love, and we all know, is composed of 3 parts. Oh, excuse me. There's the Java language, the core libraries like Java util string, Java lang string, hash map, all the kind of built-in core libraries that you have with Java. And then there's the JVM. So there are 3 parts. And primarily, this talk is about this part, with a bit of this part and a small amount of this part. But really, when you're writing Java, the language, you shouldn't need to care whether it's running in a container or not. That's not your business as a Java writer. So what are the characteristics then of the JVM at runtime? It's a managed runtime for JVM bytecode. So you compile your Java code to bytecode, give it to the JVM runs it somehow. It's hardware and operating system agnostic, so you don't write for your Java for a particular operating system if you're using pure Java. Java specification provides a threading model and a memory model, which is consistent across different operating systems, right? And this is kind of the appeal of containers as well, that you can take a container image and run it in different places. So there seems to be some similarity between the containers and the JVM already. The next thing, runtime adaptive. This is a term used by the Java platform group at Oracle to, and other JVM engineers to refer to the fact that it's a stable execution environment. So if the hardware is not stable, if you're running on some kind of elastic cluster, still the JVM should present you a consistent and reliable view of the underlying hardware, right? So it sounds like this is a good fit already, because you can take a container and run it anywhere, but you can also take Java code and just run it on a JVM anywhere. So why would you want to use containers? Because they have a very uniform model, start, stop, kill, right? You can put whatever kind of process you would like in a container, and this is where the shipping container metaphor is like kind of accurate, because they all kind of fit together. You can use the same tooling, and a lot of the cloud providers will provide you tools for dealing with containers, where they won't provide you tools for dealing with like your particular setup of your Java application. If you can fit it into a container, you can deploy it, and it will work with their tooling, right? So what do we want from Java in containers? I have three things I want from Java in containers, right? And I used to work on cloud infrastructure projects. In previous jobs, I've worked on functions as a service. It's like a serverless thing for running Java. And I've worked on public cloud infrastructure and running other people's Java as well as possible. The things that I always wanted were fast startup of the JVM, small container images, and respecting the environment. So this sandbox context of running in a container is not the same as running on the host. There are important differences, and your Java process needs to be aware of them and to deal with them. I'll talk why that's not so scary as it sounds later. So that really is going to be like the structure of the rest of the talk, okay? We're going to talk about fast startup first. And why do we want fast startup? This is a survey done by a company called Datadog about container usage. And they found that orchestrated containers, so people who are using Kubernetes, who's using Kubernetes with containers here, right? Who's using containers without orchestration? A few. So most people who use containers are using orchestration. So production containers have a mean lifetime of half a day with a managed thing like Kubernetes. An order of magnitude slower would be unorchestrated containers, and another order of magnitude slower than that is uncontainerized applications, where you used to start it and leave it running for days and days before rebooting. And this is only in production, right? We've also got build, we've got test, we've got CI environments. Everywhere where containers are involved, they are restarted more frequently than processes that are not containerized. So we're really not interested in waiting around like 20 seconds for a Java process to start. It doesn't sound like a lot by itself, 20 seconds, but it adds up because they get moved around, rescheduled, orchestrated around the place. So what can we do? There's a few tips here, but they all boil down to this same thing. Things that happen at the startup of your application could happen when you're building your image, right? The Micronaut people know this. The Quarkus people know this. If you went to either of the Quarkus talks that's happened today or the one yesterday. So let's talk specifically about how to do that. Class data sharing. Hey, who's using Java 8? Cool. Who's using Java less than 8? Excellent. Nobody. Who's using Java 11? or like 8 to 11. Okay, and newer than 11? Hey, all right. Okay, so class data sharing is a thing. Who knows class data sharing, actually, whilst we've got hands going up and down? Okay, good. This is a thing that's been in Java since Java 5, so it's almost old enough to drive a car, right? It's 15 years old feature of the JVM. Class data sharing caches the result of loading core Java classes. So what does that mean? I'll show you. Let's jump over here. I have, so I'm only talking about JVM startup. I'm not really talking about your application startup because it's only core classes. So I've got a program. I'm just going to shrink that a little bit. Can you all still read that if I just shrink that down? A simple Java program, right, to exercise starting up the JVM. I'm going to compile it, Java C hello.java, and I'm going to run it, Java hello from Matthew, that's me. How many classes do you think were loaded by the JVM in the time it took to run that hello world? Like more than 50? Less than 50? More than 100? Oh, all right, I'll show you because I already know the answer. With Java, this is Java 8, so I can use -verbose class. And you can see there's one line, which is my output, and the rest of it is classes that have been loaded from rt.jar. How many of them? 387, if you take away one for my class, right? So there's a lot of classes loaded at startup. And what happens? Where are they coming from? They're coming from here. This is Java 8 again, remember, before modularization. They're coming from rt.jar. This means they are stored in a zipped up file on your disk, and inside the zip file is bytecode. So the JVM has to load the file off disk, unzip, parse the bytecode, and build in-memory data structures representing each of those classes before it can run your code. And the thing is, the result of doing that is exactly the same every single time. So why can't we do that once, build it into the container image, and then we won't have to do it at startup every time? Answer, we can. That's what class data sharing is. To use class data sharing, -x share on. Oh no, there is no such cache of that stuff, right? What this helpful error message doesn't tell you is how to create that cache. So I'm here to tell you right now, you run -x share dump. It's finished already, and now it's working, right? How much time does that save? I'll show you. There's a tool for Linux called perf, which pulls timing data out of the Linux kernel. I've written a little wrapper script for it that runs a process 50 times and does some aggregate timing statistics. Okay, so perf 50, that, and we'll do it with it off first. Oh, crap. Pardon me. Off. Okay, so this isn't actually too bad. This laptop's quite new. It takes 41 milliseconds to fire up, load all the classes, do all that stuff. With xshare on, right? So it's like a quarter faster, and that will scale with the resources that are available, right? So you can expect from JVM startup to save about a quarter of the time if you just run -xshare dump in your Docker build and include that file in your image. Which file is it? It's this file here. It's called classes.jsa. And it appears in Java Home /jerry lib server classes.jsa, right? And how big is it? 20 megabytes. So I'm contradicting myself because I said we want small images, and now I'm showing you a technique where we're caching something and generating 20 megabytes more data, and then adding that into the image. So it's a trade-off, and it's with all trade-offs, it's up to you to measure. I can't stand here and tell you this is definitely better than the other way. But there you go, 20 megabytes versus a quarter of the JVM startup time. Yeah. Next thing you can do is application class data sharing. And this is exactly the same technique, but applied to your classes. And so the benefit is entirely dependent on the size of your application. I have one class in that application, so there's practically zero benefit, and I'm not going to demo it. People who use WebLogic and other large application servers have seen whole minutes of startup time and hundreds of megabytes of memory usage. Because remember, if you do this in a layer of a Docker image, then that can be shared between different applications. So application class data sharing, which is incidentally switched on by default in Java 13. If anyone reported Java 13, I don't think you did. Oh, no, one person did. Then you get application class data sharing kind of for free, but it happens when you run your application. So you need to run it and then bake that file that it's created into your application. I won't go into the details, but I have a blog post which I will include in the information I send out on Twitter later. So here's another thing we can do at build time. We all know, I hope, that some people here will know about the just-in-time compiler, the hotspot compiler, where when you first start running your application, it's working in interpreted mode. It takes a bytecode, it runs it. Takes a bytecode, it runs it. Takes a bytecode, it runs it. After, by default, 10,000 times through a particular section of bytecode, that will be eligible for compiling to native code. Then the compiler, the JIT compiler, will compile that, and then the JVM will swap in the compiled version for the interpreted version, and will hopefully be much faster. Well, can we do that at build time as well? Wouldn't that be like an amazing time saver? The answer is yes, we can, and yes, it is, but not without some trade-offs. So let's try it, and then I'll discuss the trade-offs. The tool I'm going to use is called Native Image, and it's part of the Graal distribution. So I'm using a tool called SDKman. Does anyone love SDKman? Yay, SDKman is amazing. If you need to work with lots of different versions of Java, use SDKman to switch between them. Because now I'm using Graal, whereas before I was using Java 8 OpenJDK. Now, if I run the tool Native Image, create a static binary from the hello class. Off it goes. It takes a couple of seconds, but it's only a small thing, so it won't take that long. And it creates this file here. This file is 3.6 megabytes, and works the same. But it doesn't need a JVM. It's already entirely compiled to native code, and it's a completely standalone thing, right? So let's time that. And let's see how fast that runs. 50 times, remember? OK, so it's like an order of magnitude faster. There is a Quarkus profile for building your tool with native image. And we've got a much, much faster startup. I don't know if you noticed this on the right-hand side as well, but we also have a much lower level of concurrency, because the JVM does some concurrent things at startup, whereas this doesn't need to. Thank you. The trade-offs are that we have lost runtime profiling information, where the hotspot compiler can take information about how your process is being used and recompile it to be faster, to make certain assumptions about which branches are taken more often. We've lost that. And we've also lost the kind of high quality of and high performance of G1 garbage collector. So the garbage collector that's included in this small application is part of a thing called SubstrateVM, and it's roughly equivalent to the serial GC that was the default a long while ago, and this still is the default in very small working environments. So for fast startup and for maybe serverless applications, have a look at native image. Another thing is it will do static analysis of your code when it's building it, and if you're using reflection, then it may be necessary to list out all the classes that it will need to load at runtime that aren't statically reachable from your code. There's lots of information about how to do that. Look at Quarkus and look at Graal itself. Awesome. Yeah, so we've seen 3 different ways of basically doing the same thing, moving startup activities to image build time. And depending on your circumstance and your particular needs, you can do one or the other. So let's talk about small images. And why do we need small images? What is the reason? Well, firstly, images get copied across the network all the time. It's easy to create a 1 gigabyte Docker image. For Java, on a very fast network, a gigabyte might take 8 to 10 seconds to copy, and it needs to be copied everywhere. The images need to be stored in places, right? So there's a storage cost as well with big images, and there's a startup cost. Even if the image is already local, there's the cost of possibly uncompressing the image file and of creating that copy on write layer. So even with a local image that doesn't need copying across the network, a small image will be better. Fourth thing, down the bottom, security. So Brian Vermeer is from Sneak. I think his talk was earlier today. He talks about how to exploit processes that are in containers. Let's have a think, right? If you use Ubuntu as a base image, the Ubuntu 1804 image ships with 89 packages installed. This is the list of CVEs against one of those packages. And it's not the case that any of those may be like very easily exploitable, but there's a lot of them. And how can you audit that? It's very difficult. The advice is like keep everything you don't need out of the image for all these reasons. I'm going to talk through a few ways of shrinking down images right now. What goes into an image? So there's a few things. Basically, as I said earlier, all of the files needed to run your application, right? So you need your application code, you need the JVM, you need the JDK, you need some operating system stuff. Let's go through this. By default, there's a kind of Java-lang object which everything inherits from, and in Docker image terms, there's a thing called Scratch, which everything is based on. This is an empty container image, and if you put something in Scratch, all it has is access to the binary APIs for the Linux kernel. OpenJDK does not use those directly. OpenJDK is compiled against a thing called glibc, which is like a Linux kernel API. glibc is included in most Linux distributions, but most Linux distributions are large compared to Alpine Linux. Alpine Linux, does everyone know Alpine Linux? Anyone using Alpine? Sweet. OK, Alpine is specifically designed to be small. And that makes it a great candidate for being used in your Docker images for Java. But there's a catch. Alpine does not include glibc. It uses a different one called musl libc. So if you get an Alpine image and you put OpenJDK in it, it won't work. Two answers. One, go in and rewrite all the code in OpenJDK to use musl libc APIs instead of glibc APIs. Someone's done it. It's not available as like a GA release, but if you look up Project Portola in the OpenJDK website, you'll find that that does exist. Different approach, as taken by the Adopt OpenJDK people, is to use Alpine Linux and install a glibc kind of compatibility library into the Alpine base. Right? This adds a little bit of size to Alpine, but not enough to make it as big as other Linux distributions. So this is what Adopt does. And let's have a look at the effect of it. I've got some JetBrains going on. Right, here's this Docker file that we saw before. From Adopt OpenJDK 11, I've written a little web server using Spark Java, which I really like as a simple web server. And it does this, right? I'm not going to build these in real time because it takes a while. And it depends on conference Wi-Fi, which I'm not sure I trust. So I've already built it, and it's Docker images -a grep for, I called it example 1. Right, so already I've created, over there, a 0.5 gigabyte Docker image. All the way over here. 446 megabytes, just like this. Here's another Docker file. Can you spot the difference? 1 and 2. 1 and 2. There's a difference here, right? I built this one. It's called example 2. 342 megabytes, right? So it's already a quarter smaller. It's over 100 megabytes smaller. And all I've done is removed things that we weren't using anyway, right? So switching the base image has saved a quarter of network copy time, a quarter of storage space, and a quarter of the image like unpacking onto disk setup time that happens. That's helpful, isn't it? Top tip number 1, use an Alpine base image. What else goes into an image? Core Java libraries. So this is going to be for those who are using Java 9 or later, after the modularization of the JVM that happened with that. There is a tool called jlink. which can help with managing the modules that your application uses. I'll show you it right now. This is, this is not intended to be readable, and it really isn't. This is a diagram of part of the relationship diagram of Java modules, right? Java 11 ships with nearly 100 modules. How do I know which ones I actually need? Can I not just remove the ones that I'm not using? Like, isn't that the point of modularization, that I can draw these dependencies out? Yes, it absolutely is. There's a tool, and I'm going to need to switch to 11.05. There's a tool in Java 9 and greater called JDEPs. So I built that application already. It's in the target directory, Spark demo, JDEPs, -- print module deps, target. Now, I'm not using modules in my project, but JDEPs can use static analysis to work out which modules are needed. And it tells me that many, right? That is 6 or 7 different modules out of the nearly 100 that ship with Java 11. I don't need the rest. Why am I including them in my Docker image? Good question. Time to introduce tool number 2, jlink. Jlink can take a base of where you've already got Java installed, a list of modules, and it can produce in a directory that you specify a new distribution of Java with only those modules you need. I'm not going to type it out because it's quite long, but I've got it in my history here. Jlink, this is the directory I'm putting it in. This is where the modules that it's getting, that it needs, it's going to get those from. And then these are the modules I need. Run it. And there you go, it's finished. And now I've got my JDK, and it's got bin/Java, whatever. This is a whole installation. I don't need the one that's in my Java home now if I add my JDK to an image. So how much space has that saved? Let's have a look. Java home was here. And that was 311 megabytes. Oh, goodness me. du -sh. The disk usage summary in human readable format of my JDK, 91 megabytes, right? So there's another 220 megabytes that was included with the Java I downloaded that I do not need in my application. Over here, Docker file number 3, I've chosen, you could equally do that in Docker build, but I've chosen to just say, all right, I've done it outside. And then I add from a Ubuntu base image, my JDK, the jar file, and the command that I need. And now we're down to 161 megabytes, right? So we've taken about 2/3 of the image. And again, we're just removing stuff that's not needed. OK, so we saw Alpine base image, and we saw jlink on Ubuntu. Why not both? Yeah, why not? It works. But I apologize in advance for this Docker file, because it's not beautiful. The reason is because you need to start with an Alpine base image. Here it is. There's no way you can read that. But this says from Alpine. And then there's this one command here. And this I've copied from the OpenJDK Docker file. This is one command. It corresponds to one layer in the Docker image. And this adds the glibc compatibility layer. I will definitely include this in the links I put out in the slide, but I'm not expecting anyone to read this and copy it right now. Then, anyway, add my JDK, add the jar, set the command, and that is image number 4. So it's another 50 meg off, right? So we're less than a quarter of the original size, and by using jlink and Alpine, all I've done is remove things that I don't need. So this, if I run it, will have exactly the same behavior as the full, like, ½ gigabyte image, but it's a fifth of the size. So it's about a quarter of the size, let's say. OK. What's next? The JVM. Of course, we need a JVM for running Java, but I showed you earlier something which can create a small binary, including a thing called SubstrateVM, and exactly the same you can do with the jar file, right? So if I run If I switch back to using the Graal and use native image again, native image, blah, 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 dash jar and this, then it will create a native image of that jar. It's a little bit slower because there's more to statically analyze, but it does it in like less than 10 seconds, I'm going to say. So I'm happy to wait, if you're happy to wait. Please. Awkward silences are my jam. Come on, come on, come on. OK. It says 26 seconds. I don't think it was that long. That might be parallelized. Anyway, it's created this Spark demo snapshot, which is 16 megabytes in size. Starts the web server in 8 milliseconds. And because I specified when I created it -- static, that means it has no dependencies on any other libraries, including glibc or musl. So when I want to create a Docker image of it, I can literally say, from scratch, add that file and run it. So we saw that that binary that was created was 16 megabytes. The Docker image that's created is like 17 megabytes, because there's some overhead in the image, Docker image format. Again, though, we've lost, at the cost of very fast startup and very small image size, we've lost good garbage collection, very highly performant garbage collection, and we've lost runtime optimizations, which means we've lost peak performance. It's a trade-off. You make it yourself. Last thing. Oh, SubstrateVM is the name of the VM that's included in these binaries. You can find details about it on the Graal website. Last thing that goes into the image, your code. Okay? And if I am going to give you any advice about how to have a smaller image size with reference to your code, then my advice has to be this: write less code. Okay? Or add fewer dependencies. Do you really need to add like a 20 megabyte util package when all you need out of it is a single method? I'm not going to tell you to copy and paste a single method off of someone else's code base, but just be aware that adding dependencies to your project carries a cost in terms of the size of the image, which has a lot of other bad effects when you've got larger images. It all adds up. Okay? And primarily, yeah, write less code. My favorite days as a programmer are when I go in with some code and I finish the day with less code. I feel that's very productive. All right. Last point then. Let's talk about respecting the environment. So the sandboxed environment that you get when you run a process in a container is different from the environment you get when you're running not in a container. How so? Quite noisy, isn't it? So the JVM self-tunes based on what it can detect of the environment that it's running in. So memory, CPU count, exact CPU model, and a few other things. The JVM will detect those and automatically tune or configure itself through a process called Ergonomics. I don't know if you can all read that because it's like near the bottom of the screen. But so Ergonomics is very powerful, right? You've all used it because you all run Java, blah, 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 and you expect the heap size to somehow match the amount of memory you have. And the Ergonomics is taking care of that. So let's see particularly what Ergonomics does based on the CPU count. Ergonomics selects thread pool sizes, garbage collection, and compiler thread pool sizes. And it also affects this method here, runtime.getAvailableCPUs, which is used in lots of libraries. It's used by the fork join pool in Java to size the thread pool. The idea is that if you have 8 CPUs available, then you can do 8 things at once. So you should get 8 threads in a thread pool if you don't want them to be blocking each other. With Docker, one of the things you can do is pin a container to a subset of the CPUs that are actually there. And if that happens and get available CPUs returns like 64 on a big machine, but you're actually pinned to 2, then suddenly you're creating 32 times as many threads as there are CPUs, and you will have a lot of contention. This was a big problem in the past. Based on the detected memory, Ergonomics will, like I said, it will select your heap size for you, how much memory you have, available to create objects. It will also garbage collection region sizes and other memory pool sizes selected by Ergonomics based on detected memory. And again, Docker can limit the amount of memory that your process has available to it. Also, this one. This is sneaky, right? Which actual garbage collection algorithm is used depends on how much memory is available. I was surprised when I learned this because I thought modern JVM, the default GC is G1 GC, and that's how it is. But it's not. The default is dependent on how much memory you have. Containers, like I said, from using Docker, containers can have restricted memory and CPU from the host, and this is not transparent. Right? The JVM needs to know that that might be the case in order for Ergonomics to work properly. But there's good news. This is not your problem. This is the problem for the people who write the JVM. The Java virtual machine engineers at Oracle and Red Hat and IBM and SAP and all the other companies are aware of this. And Ergonomics support for containers has been in every release since JDK 8. So if you're using a later release of JDK 8, you're good, but it's been improving ever since. I'm going to show you an example. So, oh no, I want to open this. There's a flag for the JVM called -xx print flags final. Okay, and this prints out, how many configuration parameters do you think there are for Java 11? Let's have like another quiz, another guessing game. More than 100? More than 200? More than 300? Let's find out. I actually haven't checked this, but there's a lot. So I've got a container image here, which just runs OpenJDK 11 on Alpine, and it just runs that, and it does dash version, because you have to tell the Java virtual machine to do something, otherwise it gives you a long, long error message. And I built that image as example 6. So let's run it. Docker run example 6. Whoop, off it goes. Let's shrink that down. Just, I know you won't be able to read it, but just to get an idea of how many there are. Right, so each one of these is a parameter for the JVM that you can set if you want to. I won't recommend doing so most of the time. Good gosh. OK, so there are 3 lines of output at the end. So let's take away 3 from the total of 669. Right? So there are over 600. Sorry, I'll bring that up because you can't see the bottom of the screen. 669. Here. So there are over 600 parameters that you can use to choose to tune the JVM. I highly recommend you leave almost all of them alone. Trust Ergonomics, trust the defaults. If you do change any of them, and then you change your Java version, test whether they have the same effect as they did before, because the defaults and the behavior of Ergonomics changes from release to release as well. So how many of those are set by Ergonomics? Let's have a check by grepping for Ergonomic. I need to make it a little bit smaller, but that is how many of those are set by Ergonomics, right? But it's not very many, and they're all things like you would expect based on what I just said. The thread pool for the compiler, the initial heap size, another memory pool, whether to use compressed object pointers or not. But this one is very, very significant. It says use G1 GC, and it's set to true. If I docker run -m 1024 meg, so I'm restricting the container to 1 GB of heap, which sounds like a lot to me, but then suddenly that's gone, and we have use serial GC equals true instead. So it's very important that you understand this, that which garbage, because these have very different behaviors at runtime. Serial is stop the world garbage collector. G1 GC can progress with collecting garbage at the same time as your application can make progress with responding to web requests or something like that. So I recommend highly that you leave Ergonomics alone and trust it to do its job, except with the possible exception of choosing which garbage collector to use. If you're using Kubernetes, you can specify resource limits, which can then turn into memory limits for containers. So this is a partial list of improvements that have been made to the JVM since Java 8 for detecting and supporting being run in containers. Okay, there's stuff like the C group memory management limit. That's what I've just demoed. JCommand and JPS. If a Java virtual machine is running in a container, then external tools that need to attach to it using the attach API need to behave differently, right? So there's a lot to it, but you don't need to worry about this. If you use the most recent version of Java that you possibly can, you will just get improvements release upon release. So this is my summary slide now. The fact is that container usage is, and has been for a while, becoming more and more popular, and the Java engineers at Oracle and all the other companies are well aware of this, and in order to keep Java as popular as it is for server-side applications, they're responding by making sure the JVM works well, making sure that there are tools available to build small images, and working on startup time. So there are whole teams dedicated to this stuff. Because in the world of containers, we still want Java to be as popular as it was in the world 20 years ago of like big, long-running WebLogic servers or this kind of thing. That then concludes this. I hope it's been interesting and useful for you, and I'm happy to take questions either here or there, like afterwards. There's still Twilio stickers there. And like I said, I'm on Twitter, and if you follow me there, you will see the slides, the Docker files, and all the code I've shown will be up in probably like an hour, just after I've finished tidying up and removing all the comments. So thank you very much.